Okay. Even if you're not sure, just put whatever comes to the top of your head. I'll give you a few more seconds to get your answers in. Okay. Most people think there are around three forms of water that we currently know of, right? Can anybody, Emily, do you know do you want to name those three forms that people might be talking about?
Is it solid, liquid, and gas?
Okay, solid, liquid, and gas, right? Simple enough. So you have solid in terms of ice, you have liquid in terms of water, and you have gas in terms of steam, right? So a very simple picture, but actually, if you look more deeply at the technical definition, it turns out that there's tons and tons and tons of different forms of water. We might be familiar with the area around here, right? With our familiar form of liquid water. Although people kind of debate how many forms of liquid water there actually are phase of vapor and the familiar ice that we see. And this type of ice we encounter basically is pretty much the only type of ice most of us will see unless we work in some sort of weird laboratory. But if you expand your mind a little bit and look at other conditions, you'll find that actually there's a ton of different forms of water, especially when you look at solid forms of water, right? Um, and they have all sorts of weird properties, especially if you really go into extreme conditions. Then you'll have water that behaves as if it's a metal, water that behaves as like a superconducting fluid, and water which has other weird properties such as you'll have there's this really cool form of water that's completely solid, much denser than any form of ice you've ever encountered, and it's jet black. So um, it could do all sorts of things, and it could behave in all sorts of ways that you scarcely imagine, which is pretty impressive for a molecule which is so simple, right? um, but it's this flexibility which allows it to really permeate all aspects of our life. And it's these properties that really influence how biological life is set up, how it's structured, and in turn, organisms take advantage of these properties of water for its own benefit. And the reason is because biology is mostly chemistry in a water background, right? Most of our reactions, or almost all the reactions of life, occur inside a solution of water. And there's a couple of distinct properties, some of which I've gone over in the previous lecture, that allow water to facilitate this chemistry. One of them being the polarity of water. For instance, you have a positive charge on one end and a negative charge on another end due to the different electronegativity of the atoms of water and the hydrogen bonding that it could undergo, which allow it to not only interact with itself, but also interact with other substances that may be inside the solution. And this is where we jump off into the concept of hydrophobicity and hydrophilicity. Hydrophobicity, it means a substance which tends to repel water, right? If you have a raincoat is designed covered in hydrophobic, at least most of them are covered in hydrophobic substances, and these tend to repel the water drops. Or you, on the other hand, you have a hydrophilic substance, and these substances, they love water, so to speak, and that means they like to really interact with it and mix inside the water. Um, these are kind of imprecise terms. You can more kind of think of them more as how well a substance can be dissolved in water, and how well it's dissolved ultimately is up to how well water, in what fashion water interacts with it, and also how well the way it interacts with it contributes to the increase in entropy. So does anybody remember what entropy means from high school physics or physics if you've already taken it? How about Ethan? Ethan, do you know what entropy means? Do you want to give me a definition off the top of your head? Any sort of definition? Okay.
Can you hear me?
Yes.
I'm not too sure. Is it like heat or energy?
Yeah, you could think of it as heat, right? So you could think of it as heat, and on a molecular basis, it's um, a measure of disorder, right? So, which heat in some situations is, it's a measure of disordered particles. Particles are just flying around and they're not really moving in any particular direction. So when you're talking about entropy in a molecular system, you want to move in the direction of more disorder, because according to the laws of thermodynamics, things generally progress from a more ordered state to a more disordered state. And that makes sense, because if you have, for example, you have a dirty room, you're typically not going to come back one day and just suddenly find it spontaneously rearrange itself so that the room is completely clean, all your clothes are folded and put away, right? It usually doesn't happen that way. Okay. So that's ultimately whether something's hydrophobic or hydrophilic, depends upon these characteristics. And speaking of that, does anybody know what this structure is right here that I'm pointing to? What would you call that structure? Lipid bilayer, right? So lipid bilayer, you have it's present in cell membranes. Cells use it. Organisms, single-celled organisms, use it to keep all their stuff away from the external environment, to kind of delineate their boundaries, right? So I'm gonna ask you, what is so special about this lipid bilayer? And you should see another question pop up on your screen. Okay. Give people a few more seconds to get their answers in. Okay. Does everybody agree with that answer? Do you think it's correct? Well, most people agree, right? Um, oh, you don't see the poll? Right. Well, most people pick the third option, if in case you can't see it for some reason. Um, they we the lipid bilayer is both a hydrophobic substance and also a hydrophilic substance. Um, what part of it is hydrophobic? do you think for the lipid bilayer? The tail, right? So the inside of this is hydrophobic, and the outside of this is hydrophilic. You have the tails on the inside burying themselves, trying to avoid water, or the hydrophilic part is outside, it's interacting with the water, and it's completely fine with it. Okay. And you'll see this behavior, you'll see the basis of this behavior in the subsequent slide over here, where we dig a little deeper into why it's behaving that way. If you have a hydrophilic substance, you're surrounded by water molecules, but the water molecules can interact with the substance, right? So it's not really shown here, unfortunately, but it's gonna bond with the substances, and it's gonna gradually form these shells around the substances known as hydration shells, right? So the hydration cells will come in, they'll form, and then they'll break off piece after piece, and then gradually they'll carry off more and more away until the substance dissolves. And this is the way for the system to maximize the entropy, to increase the entropy in the system, right? This is the more energetically favorable way. It's the way for it to reach the most energetically favorable conformation. If you have a hydrophobic substance, on the other hand, instead of interacting with it, the water molecules can't really interact with the substance. They don't have anything to glom onto except themselves. And what this is going to do is it's going to cause the water molecules to form this giant non-interacting cage. Well, non-interacting with the center. They could still interact with themselves, but this cage surrounds it. And this cage is very unfavorable the larger it gets. So since it's like really unfavorable when it becomes large, what's going to happen is that this center is going to be jostled in a fashion that it's going to fold into itself to of minimize the surface area that's exposed to the water. So the water is going to want to bond with itself as much as possible and bond with this as least as possible. So it's going to end up crushing this into kind of a bit of a ball. And you see that when you're looking at grease, right? You're washing your dishes, and then you have big globs of grease, and the water doesn't really dissolve it at all. The water just sits in one place, and the grease just sits in another place, and they don't really have anything to do with each other at all. Yeah. So that's hydrophobic. This is hydrophilic. Keeping these two things in mind that I just told you about, and this lipid bilayer, can anybody tell me how soap would come into the picture? If for example, you had a big chunk of grease, right, and you try to wash it off with water, and the water doesn't do anything, how would soap come in and help you end up cleaning off the grease? What would happen based upon what I showed you here in molecular terms? Does anybody want to take a guess? What does the soap do to the grease that the water can't do? Yeah. Okay. So it's partially polar and it's partially non-polar, right? So soap molecules are kind of like this, kind of like these molecules. They have a polar portion and they have a non-polar portion. They have they have a portion which is hydrophobic and hydrophilic. So what these end up doing is that they end up kind of like coming in like daggers, so to speak, and then the hydrophobic portion can interact with this glob. So it starts to, if you have many of them around, they start to form cages around the molecules, just like the water can. And then they start out breaking piece by piece. So gradually the grease dissolves. And then, yeah, the grease dissolves and is eventually carried away more and more until the grease goes away. And then your dishes are clean because you added soap. And your laundry is clean if you add detergent, right? So it's really helpful. Um, So you weren't doing it wrong just because you couldn't get the dishes clean with water alone. I don't know, like I was told when I was a kid, where I tried to clean my dishes with just water, and people got angry at me because I couldn't clean it, and they didn't know that it's not just a matter of not trying hard enough. Sometimes you just need like a little bit of the right chemistry on your side to actually do a good job. Okay, so sometimes it pays to be more intelligent about these things rather than just trying to work harder and not really think about it at all. But enough about that. Another thing that's important about water is how acidic or basic it is, and that leads us into our next question. What do you think would be the definition of an acid and a base? Do you see the question pop up? Another question should pop up. Okay. Get your answers in over the next few seconds. All right. Okay. So most people pick the third option. I'm not sure if you could see the poll results or not, but most people pick the third option, right? So when it comes to acids and bases, actually there are several different definitions, related but different nonetheless, definitions of acids and bases. But we're just going to go with these initial two for our purposes. You could think of acids um, as substances which generate the H pluses in water and which donate these H pluses. And you could think of bases as substances which generate OH in water and accept this H, um, accept these H's. And when you're looking at pH, if you have a lot of these H pluses, the pH will go down. Whereas if you have a lot of these OHs, then the pH would go up, right? So higher is more basic, lower is more acidic. And it might seem like a very trivial thing, but actually this could have a really radical effect on different organisms. Because if you think about it, your body, it consists of a number of very complex molecules, like for example, proteins. These aren't just, an atom here or an atom there. What they are these hyper complex machines, and these machines are in complex with other machines. So you have these really finely tuned factories. And these finely tuned factories, they need to have a specific set of conditions, right? And if something goes wrong with those conditions, they could stop working or be destroyed. And that's exactly what pH does if it goes too low or if it goes too high. On the other hand, if you have an ideal pH, you might actually increase the efficiency of these machines far more than you would if you had slightly different conditions. So pH is very important aspect in biology, very important to make sure that the environment is just right in order for certain chemical reactions to go the right way. Okay. Related to this is the concept of buffering. As I mentioned just right now, pH is very important. in certain situations, if you're talking about industry or if you're talking about your body, you don't want the pH to change too drastically. And if you've taken chemistry before, you're doing your experiment with working with acids and bases. So it's very easy to mess up the pHs, right? You could add a drop of something and then the pH will swing wildly in the wrong direction. Well, to solve that problem, that's where buffers come in. You have these tiny little pink particles that could be considered buffers, for instance, and then you have these, for example, OH molecules. You add these in. Normally, these OH molecules might cause the pH to drastically go up, but these pink particles, they donate hydrogens, they neutralize the OH, or at least part of the OH, and so the pH doesn't rise as quickly as you think it might, right? So it provides a buffer or a sponge to soak up the pH changes and have things not change as drastically as they might otherwise change. Okay. So that is the sum total of what we're going to go over today for the water. Does everybody understand that? Does it make sense? Any questions at all? Any questions or concerns or corrections? Nope. Okay. All right. If nobody has any questions, we'll move on to working with our worksheet. The worksheet for today. Let me see if I could bring that up. Sorry, this kind of is a little bit of a clumsy interface here. Worksheet. Okay. You could see the worksheet, right? Yes, no? Okay. Worksheet. Gosh. So we have our molecule right over here. Does anybody know what this molecule is called? Bridget, do you know what this molecule is called?
I don't.
Okay. It starts with an E. Thane.
Oh, wait, sorry.
Starts with an E, right? So the one carbon would be methane, right?
Mm-hmm.
And since it starts with an E, what would this be called? The one carbon is methane. 3 carbons is propane, and this starts with an E, so what would it be called? Ethane, right?
Ethane.
Ethane. Okay, so this would be ethane. Okay, and what they want us to do is they want us to take this chain and they want us to add an amino group to it, right? And anybody tell me what an amino group is? What would be an amino group? Amino groups, kind of like amino acids. Amino acids are protein. Protein gives you lots of nitrogen. So what would that be? N2, right? N2. At least some of them do. Okay. So N2 would be right over here. And this is the molecule. You're adding an amino group to it, right? Now, what effect would it have on these different properties? For example, the polarity of the molecule. Would there be no change, increase, or decrease? Increase. Okay, why would there be an increase? By the way, if you want to unmute your mic, you could do so. That might be quicker, right? Why would there be an increase in polarity? Why would there be an increase in polarity for this molecule?
The group would cause a polar end.
Yeah, so polar end, right? So you have electrons being pulled in this direction because N is much more electronegative than the carbons, right? So you cause a negative charge at this end, right? And then it would cause it to become polar. So that'd be an increase. Okay, let's take this to the class. What would be the change in, oh gosh, it's annoying. What would be the change in solubility for molecule 1? Would it no change, increase, or decrease? Give me your thoughts. You can do this. I believe in you. Remember, think about the polarity this introduces. Think about the electronegativity and what would solubility mean in this context? Because water is a solvent, right? So if water is a solvent, what would this increased electronegativity cause? Okay, I'll give you a few seconds to make up your minds and enter in your answers. Okay. Okay, so most people think it would increase, right? Why do you think it would increase? Why do you think this would cause an increase in solubility? Because water is polar, right? So if water is polar, what is this addition going to do? Right. So it's going to interact with water, right? So this water is going to be encouraged to interact with this negative N, hydrogen bond to this negative N, and then it's going to cause an increase in solubility. Okay. Everybody with me so far? Right. What about pH? Is there no change in the increased direction or change in the decreased direction? Okay, why do you think it would why do you think it would increase? Okay, why do you think it would increase to the pH? Or why do you think it would decrease to the pH? Does anybody know? Anybody want to take a shot at it? Okay, so H is added from the amine group. What do you mean by added from the amine group? Does it come to the amine group or does it go away from the nitrogen? Right. So it's basic. Why would you say it's basic? Why would you say it's basic? Okay,
It contains a lone pair of electrons.
yeah. So what is that lone pair gonna do? Might
Um, it increases. Wait, like,
okay. So this lone pair might grab a hydrogen, right? And what's that gonna do to the pH? Would it cause it to increase or decrease?
increase.
Okay, increase, right? Because you're taking away hydrogen, so kinda. Okay. Now let's look at the addition of another group, a methyl group. Okay. So does anybody know what a methyl group is? Kira, do you know what a methyl group is?
Not off the top of my head at the moment, no.
Okay. So a methyl group consists of a C, right? A C and a carbon, and what else would it consist of? So you have a C right over here. What else should I put on here? Kira, what are these other atoms that surround the C?
H?
Yeah, so H's, right? And this would transform this ethane into propane, right? Everybody agrees with me? Propane, I think, three carbon chain. Anybody watch King of the Hill? Okay, I guess not, right? Okay, moving on. Right, so you add this CH3 into the substance, right? What is this? What does this do to the properties of the molecules? What does it do to the polarity? Would it increase it, decrease it, or have no change at all?
No change.
No change, right? And why would you say no change?
It's already nonpolar and the methyl group is still nonpolar.
Okay, yeah. So carbon not really gonna pull much more from the. They're all equal electronegativity, so there's no net change in the pull, so no change. Okay, what about the solubility? No change, increase, or decrease? This is actually kind of harder than it looks, right? Because the solubility of this is terrible, and the solubility of this is terrible, right? It's like in most cases, for all intents and purposes, they're kind of insoluble in water, both of them, because they're more like a gas substance, so you're hardly going to see any dissolve at all. There's a little bit of move, but based upon what I read, I would kind of put no change, at least for now. If I find something different, of course, I'll let you know this guy. But they're basically kind of both insoluble at all, and adding this additional carbon group doesn't really change much at all, right? This is a terrible solute, and this is a terrible solute. Yeah, so that's that. I'll update you if I find something differently. But okay, moving on to the next one. pH of solution, no change, increase or decrease, and I'll throw this out to the entire class. Would it change? No change, increase or decrease? Remember what we think we're talking about when we're talking about pH, right? pH has to do with the hydrogens and the hydroniums. Do you see any change in those dynamics if you add this extra C on there? Oops. Pause. If you don't know, just think of as something on the top of your head. Maybe inspiration will come to you when you least expect it. And I'll give a few more seconds to get your answers in. And okay, most people think no change, right? Most people think no change, and they would be correct in that when they say that. You add another CH3, you know, you're not really going to get changes in OHs or Hs, so no real change in pH. Okay, moving on to our next couple of molecules that we need to look at. Okay, so we have the same thing. We have a CH and a CH, right? And then we need to draw a new molecule that will increase the water solubility of this. So what can we do? What could we add in there that would increase the solubility? Anybody have an idea? Amino group. Yeah, that could. Good. Let's keep it simple, right? Let's make it a OH, an alcohol, right? So we have this alcohol over here, and then this might increase the solubility. And why would it increase the solubility? More polar, right? So what is it being more polar have to do with increasing the solubility? Okay, Sydney, how does being more polar increase the solubility?
Does it help form hydrogen bonds with water, helping dissolve the compound?
Yeah, correct. So you have the water coming in, and then this water can interact with this oxygen, right? And by interacting with the oxygen, by hydrogen bonding, they could begin to pull complexes of these molecules apart, and in that way, they increase the solubility. Okay? How about this molecule right over here? We want to draw a molecule that will decrease the pH of the solution. How should I start? Anybody want to help me? Anybody have an idea of how I should start? What should I draw first on here? Okay. So you want something that will decrease the pH as a solution, right? And what would you add on here to decrease the pH of the solution? What does decreasing the pH of the solution mean, by the way? Does it mean making things more acidic, or does it mean making things more basic? decrease in pH, more basic or more acidic? More acidic, right? Um, so if it's more acidic, then we want something to act as an acid, right? And what sort of functional group? Okay, somebody already put that. So yes, carboxyl would be a example of a functional group you could add. And what is carboxyl? What is a carboxyl group? What should we put it? What should I draw next to this carbon to make a carboxyl group? What is in the molecule besides the carbon for carboxyl group?
An oxygen, well, the carbon's double bonded to the oxygen and a single bond to an OH.
Okay, so you have an O here and you have an OH here, right? And then how would it be acidic? How would this act as an acid in terms of the solution?
It would donate H pluses.
Yeah, so this H might come off, right? And so yeah, that's how it acts as an acid. And then you could have water molecules interacting with this oxygen. For example, if you want to draw like where the oxygen would come in. And then you could also have it interacting with the hydrogen or interacting with this oxygen too. Okay? Does anybody have any questions on that? Is this all clear to everybody? Any questions, corrections? How do I determine what? Oh, 3? How do I determine what about 3? Okay, for 3, right? You're trying to increase the water solubility, right? So water's a polar molecule, and you want something that's kind of like the polarity of water. And the way you could do that is adding an OH in here, right? Because the carbon chain isn't really polar itself, but when you add the OH, you add an electronegative atom, which would pull the electrons toward it and give it some of this polarity. With some of this polarity, then you could start attracting water molecules to come in and interact with it. Okay? For in terms of pH, right? This carbon atom has an extra H that could detach from the oxygen and like give it more acidity. If you want a handy cheat sheet, you could look at the slide they have over here, where you've probably gotten it from lecture, but it will talk about the different functional groups that you need to keep in mind. And you look through them, right? And you see carboxyl. You'll see carboxyl acts as an acid, and you'll see an amino group acts as a base. So you'll see the hydrogen detach from over here, and you'll see the hydrogen become attached to the nitrogen. This takes away hydrogen, so it would be a base. This gives hydrogen, so it'd be an acid, right? Is that clear to everybody? Okay. I think this would be this is the entire worksheet. So that's it for the worksheet. If you have any questions, continue asking me questions, or you could ask me through email. This assignment should be posted up. You should have a due date for it, so go check that out. Turn that in by the due date, which is sometime tomorrow. And then, yeah, so if there's no more questions, you could go. If you have questions, you could ask me. Otherwise, this is basically the end of the discussion. Hope you had a enlightening period. Okay. So if you need anything to say, just like say it to me now. Otherwise, I'll just go about my own business.
From the chemical groups, how can you tell how each one affects the pH of the solution?
I don't know if you answered the question, but I think you were muted.
Hello, can you hear me? Hello? Are you still there?
Yes.
Okay.
Yes.
If you remember from worksheet 1, right? They had a table. I'm just trying to find it right now. Let me see if I could pull it up here. Okay, I can't find the worksheet, but you have this when you look at this nitrogen would have a pair of electrons on it, right? And then these electrons would be able to grab onto this hydrogen, right? And through grabbing onto this hydrogen, it would act as a base because it's decreasing the amount of hydrogens in solution. Whereas you have, on the other hand, you have this carboxyl group, and then the carboxyl like has this double bond over here, so it would play a role in stabilizing it when it would play a role in stabilizing it and allowing the hydrogen to detach, right? So, but it's not always a completely cut and dry phenomenon that you could determine based upon structure alone, because you might expect the hydrogen for the alcohol to lose. You might expect the alcohol to lose its hydrogen and act as an acid, and it does kind of do that to an extent, but not as much as the loss of hydrogen that you see on the carboxyl, right? So if in doubt, I would consult this table for the information, because I think this table is all the major functional groups that you're going to encounter in this class. So is that clear?
Okay.
Okay.
Yes. Thank you.
Um, amino group would be basic, and carboxyl group would be acidic, right? Okay. Any other questions?